when you take the delta 18 of the ice and you measure it and you plot it against the carbon dioxide for Vostok, the ice core from Antarctica, what you see is a remarkable correlation. You see carbon dioxide fluctuations, and the delta 18 fluctuates as well. In fact, in Vostok in Antarctica, they also measured the delta D, which is the ratio of deuterium, the heavier isotope of hydrogen, but it's very similar. The physics is exactly the same as oxygen. When we look at the Vostok record of temperature and carbon dioxide, we do see that they look amazingly well correlated. The temperature of Antarctica looks amazingly similar to the fluctuations over the last few 100,000 years in atmospheric carbon dioxide. What about this question of timing? How well do we really know the timing between the changes? If we look carefully, your eye tends to look at some of these fluctuations, like the one around 150,000 years ago when it looks like they're more or less perfectly the same. But your eye is also drawn to changes like around 400,000 years ago, where it looks like the carbon dioxide level drops a little bit after the temperature. On the other hand, at other times, it looks like the change in carbon dioxide precedes the change in temperature by a little bit. And so people have argued about this because they worry about the causation. If carbon dioxide is following the temperature change, how could carbon dioxide really be responsible for the change in temperature? It's a very good question. One complication is that the actual timing between these is actually pretty complicated to unravel. And the reason is that the age of the ice is actually not the same as the age of the air bubble trapped in that ice. So when we measure an ice core, we measure its gas, and we reconstruct the carbon dioxide, that gas is a little bit older than the ice that traps it. And let me explain. The way ice forms on a big glacier is that snow falls and gradually gets compacted and slowly turns into ice. This diagram gives just a schematic demonstration of that, where at the top of the diagram, that would be fluffy light snow at the very top, and you see a depth scale on the right of meters, and you can see in the upper 10 centimeters or so, it's still very light, fluffy snow with a very low density of maybe 200 kilograms per cubic meter, or 0.2 grams per cubic centimeter, so a fifth of the density of liquid water. What happens as the snow gets compacted is that the air gets pushed out, and so the density increases, going from maybe 0.2 grams per cubic centimeter up to 0.4 or 0.5. And the air spaces become more and more tight, and there's obviously more snow and less air. By the time you're maybe 10 or 15 meters down, you're getting to be very dense snow, what we might call ice, but in fact, it isn't yet really true blue glacial ice. Depending on the temperature of the column of snow, the temperature of the region, depending on the detailed physics of the snow, this can actually vary enormously. This transition between snow and ice can happen over 10 meters, or when it's very, very cold, it actually takes a lot longer, and it can happen over as much as 100 meters or more. But eventually, you actually do form blue ice, but there's still cracks in the ice. There's still interconnected spaces where the air can diffuse and connect with the air in the atmosphere above this column of snow we call the firn, F-I-R-N. Eventually, and this may be, as I said, 10 or 20 meters down, or maybe as deep as 100 meters down, all of those interconnected spaces get sealed off and the bubbles become completely trapped and isolated from the atmosphere. This is when the carbon dioxide concentration is really sealed in. But before that time, the gas is actually diffusing and communicating between this ice and the atmosphere. And that means that the ice itself that's trapping this bubble has actually been there a long time. It's been there a lot longer than the age of the carbon dioxide that's trapped there that continues to communicate with the atmosphere. We call this the ice age, gas age difference. And in Greenland, it turns out this isn't very large. And the reason is it snows a lot and it's relatively warmer, and so it tends to go through this transition from snow to ice relatively quickly, generally in a few hundred years or less. And so this difference between the age of the bubble and the age of the ice is pretty small, just a few hundred years. In Antarctica, where in Vostok, for example, where the snow accumulation is incredibly slow and the temperature is very, very cold, what you actually see is the ice age, gas age difference is very, very long, is 2,000, 3,000 years. And during the last glacial maximum, when it was even colder, it might be as long as 5,000 or 6,000 years. And so this introduces a lot of uncertainty, because when you look at these records of carbon dioxide and temperature, you actually can't be perfectly sure which is leading which, because there's an uncertainty in the relative age of perhaps as much as 1,000 years or more, because we can't determine the gas age, ice age difference perfectly and how it varies through time. This gas age, ice age difference makes it very difficult to compare the timing of the changes in carbon dioxide and the timing of temperature changes over the Pleistocene. There's a more fundamental question about what is driving these changes, and we'll talk about that next time. But from the perspective of our current predicament, I think the important thing from these records of Pleistocene ice ages is that the current change we're seeing is not only incredibly fast, 100 times faster than the sorts of fluctuations we observe in these ice cores, but we're also taking the planet back to a state that it hasn't been for at least hundreds of thousands of years, and perhaps not for millions of years. And that's where we'll start next time. Milankovitch himself was responsible for one of the most important ideas about the ice age cycles that we observe in the geologic record. It had to do with his understanding of how ice sheets grow. Milankovitch hypothesized that what's really important to an ice sheet is not cold winters, because it's always cold enough to snow in the wintertime in the northern hemisphere. What really matters in terms of growing an ice sheet is cold summers, because that allows the ice that you've accumulated over the wintertime to stay around and not melt. And that is how you would actually begin to grow an ice sheet. With that understanding, Milankovitch focused on a particular latitude, the northern hemisphere, 65 degrees north, and he tried to understand how these different cycles, the eccentricity, the obliquity, and the precession, ultimately gave rise to these ice ages. Years later, this was greatly enhanced by work of scientists who were looking at ocean sediments. Now, ocean sediments are an incredible archive of information about the geologic past. If you go to the bottom of the ocean floor and you collect a core from a ship, this is the Joides Resolution, a drilling ship that the geologic community uses to collect ocean cores from all over the ocean floor. If you collect a core and look at the sediment in it, you can bring it back, and this figure on the left shows what a core from the upper half a meter or so of sediment looks like. You can see it's relatively light in color. In this case, a lot of that material is actually calcium carbonate. And if you look carefully at it, you'll discover that most of that calcium carbonate are the skeletal remains of organisms. Most of them are algae, are calcareous algae that grow skeletons out of calcium carbonate, called coccolithophorids. Some of them are protists. They're called foraminifera, and they form their skeletons also out of calcium carbonate. Some of these are planktonic foraminifera. They live in the surface ocean, and they eat other plankton, other algae and bacteria and some other zooplankton. And some of them are benthic foraminifera. This one here is a benthic foraminifera that lives on the bottom of the ocean floor and essentially eats food that falls down to the bottom. And as you can see, this skeleton, quite intricate in its design, is actually made out of calcium carbonate, and this shell is about 100 microns, or 1/10 of a millimeter across. So these are incredibly tiny, but there's amazing detail there. Now, the chemistry of this shell turns out to be able to relate to temperature. Now, just as we talked about oxygen isotopes in ice cores to record ocean temperature, similarly, the oxygen 18:16 ratio in the foraminiferous shell also records the temperature of the ocean. When we reconstruct past temperatures from ocean sediments instead of from ice cores, we also use oxygen isotopes. But the chemical physics is actually a little bit different, and the relationship between temperature is actually the reverse. Let me explain. So for calcium carbonate, we can write a very simple isotope exchange reaction, just like what we did before for liquid water and water vapor, where in this case the calcium carbonate has 3 oxygen 16s, and it's in equilibrium with water that has an oxygen 18. And we can write this exchange reaction on the right-hand side, where the oxygen 18 just changes places. So on the right-hand side, the water now has an oxygen 16, and the calcium carbonate has 2 oxygen 16s and 1 oxygen 18. So what you see in this simple reaction is just the oxygen 18 is changing places. On the left-hand side, it's with the water. And on the right-hand side, it's in the calcium carbonate. Oh, forgot a little 2 here. Just like in the situation with liquid water and water vapor, we can write an equilibrium constant for this reaction. And it's very similar. This is just going to be equal to the ratio of oxygen 18 to oxygen 16 in the calcium carbonate divided by the ratio of oxygen 18 to oxygen 16 in the water. So this equilibrium constant at 25 degrees Celsius is approximately equal to 1.03. So what that means is that when an organism grows its shell out of calcium carbonate, the delta O18 of the shell that we measure in the laboratory is about 30 per mil enriched in O18 plus 30 per mil relative to the water in which it grew. So this equilibrium constant is actually very sensitive to the temperature of the reaction. We know that many equilibrium constants are related to temperature as an exponent just from basic chemistry. But in this particular case, Harold Urey, the great chemist, realized in the late 1940s that he could make use of the temperature dependence here to have a thermometer. As I talked about before, there's a preference in all chemical bonds for the heavier isotope. In general, stronger bonds have a stronger preference for the heavier isotope than weaker bonds. And that's the same here with calcium carbonate and water. The carbon-oxygen bond in the calcium carbonate is a lot stronger than the hydrogen-oxygen bond in water. And so as a result, in equilibrium, when you precipitate calcium carbonate at room temperature, the calcium carbonate has a higher amount of oxygen 18 by about 3% or 30 per mil or parts per thousand relative to water. But here's the interesting thing. If you do that same experiment and you start heating up the water, what you discover is that preference begins to go down. Maybe after 10 degrees warmer, it might only be 2.5%. Instead of 3%. And the reason for this is very simple, that as the temperature heats up, the atoms are vibrating more, there's more energy in the bond, and as a result, the difference in mass turns out to matter less and less. And so there's less and less of a preference for oxygen 18. What this yields is actually a very important way of reconstructing ocean temperatures in the past. It's a thermometer just based on the isotopic composition of the shell. And so when we look at records from all over the ocean floor, this graph shows 3 different sediment cores, and on the horizontal axis we see age from 0 back to 2.5 million years ago. This shows the delta O18 of these benthic foraminifera that grew on the ocean floor in 3 different parts of the ocean, 2 of them in the Atlantic and 1 in the Pacific. And you can see they're actually remarkably similar from different places in the ocean floor. That's because the ocean temperature is relatively uniform at great depth, suggesting really it's the whole Earth that's warming up and cooling down over these ice age cycles. This is not something that we're just seeing at the pole. So looking at the delta O18 of these foraminifera and how they varied over time, this really advanced the earlier work of Milankovitch into the modern age and really trying to understand how these ice age cycles related to the orbital variations. A number of scientists in the 1970s started looking again at the Milankovitch hypothesis, that it was these changes in the summertime temperature at 65 degrees north in the northern hemisphere that gave rise to these ice age cycles. And what they did was, when they combined the changes in the obliquity, in the precession, and the eccentricity, they were able to create a combined signal of radiation received from the sun that looked remarkably similar to the oxygen isotopes, the delta O18 record observed in ocean sediments. And this was taken as evidence that it was the Milankovitch cycles, these orbital changes, that were actually the pacemaker for these changes. But again, these orbital changes are so small, they don't really explain the ice ages. They just explain the timing of them. The question is, how do subtle changes in the seasonality ultimately give rise to these enormous changes in ice sheets and ultimately in temperature with 5 or 6 degree cooling during the glacial maxima? The answer has to do with the positive feedbacks associated with both the ice sheets and carbon dioxide. There is one complication to the delta O18 thermometer and calcium carbonate that we haven't discussed, which is that it also depends on the delta O18 of seawater, and that can vary over time. Think about the world today with the ocean with a delta O18 around 0 per mil, and a big ice sheet on Antarctica with a delta O18 of perhaps minus 30 per mil or so on average. Actually, in the middle of Antarctica, it's a lot lower than that. But this would include the ice around the perimeter of Antarctica, which is a little bit warmer. If we contrast that with the world during the last glacial maximum, 20,000 years ago, the seawater would be a little bit lower because there was so much ice on land. The delta O18 of that ice might also be about minus 30 per mil, or maybe a little bit lower because it was even colder back then. But the ice sheet was much, much larger, and therefore there was a little bit less water in the ocean. So the delta O18 of seawater would be a little bit higher. We think maybe about +1 per mil. But this means that there's a complication here. It means that when we observe a change in the delta O18 of the foraminifera shell, the calcium carbonate shell, there are two explanations. One is that it was colder during the last glacial maximum, and therefore the isotopic fractionation between calcium carbonate and water increased. And the other is that there was more ice, and therefore the delta O18 of seawater was slightly higher than it is today. That's a fundamental ambiguity that for many decades we struggled to separate. And it's only recently that we've actually figured out how to properly estimate the change in the isotopic composition of seawater. We think it was about 1 per mil different, and therefore we can isolate the temperature component in the calcium carbonate record.